Hello. Welcome to our lecture. My name is Peter Cabrera, President of the SFAA. Just have a few announcements before we start. First, I'd like to bring your attention to the fact that next month we will be at the Rental Museum. Make sure to grab a sheet with the map of France on your way out. The next lecture will also be on the third Wednesday, rather than the Tuesday. So remember, June 20th at the Rental Museum. We also have a star party this weekend on Saturday on Mount Chan. We have a lecture there starting, I believe, around 8:15. Then next Thursday we have another star party at the Embarcadero. Typically the city lights don't help, but with the moon and the planets out, people like looking at the moon and Jupiter. Jupiter will be rising right around sunset. We hope to have good weather for that. Then I would like to have a quick show of hands of how many members we have present today. All right. And non-members? All right, thank you. We have a few perks for members every year, and among them we have a trip to Yosemite every summer. If you're interested in camping under very, very dark skies and having a free entrance to Yosemite and camping fees waived, you can become a member of SFAA and join our trip. We also have an observatory tour in Sonoma County, just east of Santa Rosa, at Robert Ferguson Observatory at Sugarloaf Ridge State Park, coming up September 1st. And those are all my announcements. Thanks.
Asking Margaret Casey and our wonderful man who does the AV Tech work for us every month to come here, if they will please. Will and Margaret. Us to come here and start having our lectures several years ago, and it's because of her attention that we are here today. And we want to thank her. Many of you signed a thank you, for her today that we're happy to give her. I'll give you the envelope.
Thank you.
And this is one from us, San Francisco Amateur Astronomers. And it says, to the Presidio Trust, we express our appreciation to the Presidio Trust, Margaret Casey and staff, for generously hosting the San Francisco Amateur Astronomers to hold their monthly public lectures from 2015 until June of 2018. The welcome of everyone involved was greatly appreciated and will be long remembered. Thank you, Margaret. AV Tech throughout all of this time, and so he sat in on all of our lectures during all of that time, and he makes sure that the speakers can be heard and the lights are perfect. And we want to thank him with a card from San Francisco Amateur Astronomers as well. our new date is the old date. We used to meet on third Wednesdays. We did that for decades, I think, and here we are doing third Tuesday. So reset your clock for third Wednesdays from now on. In June, third Wednesday at the Randall Museum, near-Earth asteroids and space missions. Michael Bush, SETI Research Institute, will be speaking to us. Near-Earth asteroids are a population of objects that orbit the sun and can come near the Earth. In addition to scientific interest, near-Earth asteroids are important because of impact hazards, and many are targets for future spacecraft missions, and we'll hear about that on the 20th of June. Then the following month, the 18th of July, viewing the beginning of time from the most remote places on Earth. Zishan Ahmed from SLAC and Kavli Institute will be talking about the cosmic microwave background radiation science. Shortly after the birth of the universe, space was filled with a plasma that was red hot. The light radiated by that plasma has traveled the vast emptiness of space, and this is called the CMB. It's traveled for billions of years, and we're going to find out where these remote outposts are for researching it, and this is going to be an extremely interesting talk as well. Tonight, we get to hear the Saturn talk, which I'm so excited about. Matthew Tiscareno received his BS in Planetary Science from Caltech and a PhD in Planetary Science from the University of Arizona. He's a senior research scientist at the SETI Institute and also a participating scientist. He's also an imaging team associate for the Cassini spacecraft. He led the discovery of small moons embedded in Saturn's rings and is working on a number of related projects, including how moons rotate and the interactions between disks and their moons. Cassini's spectacular final year at Saturn. With his 13-year mission now complete, Cassini takes his place as the most spectacularly successful interplanetary mission in the history of NASA. In its final 10 months, from December 2016 to December 15th, 2017, Cassini has transformed itself into a whole new mission, with its grand finale, culminating in the final plunge into the depths of Saturn. The new data obtained has brought Saturn's rings, clouds, its small inner moons, and much more into sharper focus than ever before. In this lecture, our speaker will review the rich harvest of the Cassini mission, what we've learned, what has inspired us, and what we might still learn. Please join me in welcoming Matthew Tiscareno.
Very much for that introduction. It's a great pleasure to be here. Thank you for inviting me to this beautiful venue, and it was a great pleasure to have dinner with some of your members before coming here. Thank you for coming tonight. The topic is Cassini's spectacular final year at Saturn. I'll start with giving you an outline of what we'll discuss. I will give you an overview of Saturn and the Cassini-Huygens mission, and also some information about the orbital tour and the grand finale. And then I will discuss several of the science results, including the ring moons, Daphnis, Pan, and Atlas. I will talk about propellers in Saturn's rings. I will talk about impact ejectoclouds in Saturn's rings. I'll talk about a new discovery that we didn't even know about until the final year of the Cassini mission, textures in the rings, and then some more examples of grand finale science. So starting with some background and going way back, Saturn was first seen through a telescope in 1610. So this is an amateur astronomy club, so you also basically date back what you're doing to Galileo. He did not invent the telescope, but he was the first person to take a telescope and point it at the sky. And for that, he is known as the father of astronomy. When Galileo first looked at Saturn, it was one of the first things he looked at, because it was a very prominent point of light, moved among the stars. That was all they knew about it. Before Galileo turned his telescope towards it, he saw Saturn have what looked like two little appendages on either side of it. And then when he looked again 2 years later in 1612, the appendages were gone. And Galileo was completely taken aback by this. It turned out then it was Christian Huygens, in 1659, who explained why this is. He inferred that Saturn has a disk. which is stationary with respect to the spin of the planet, and as it goes around the sun, we see the disk from different angles, and that's why sometimes we see the disk fully open like this, and sometimes we see the disk edge on so that it is invisible, and that explained Galileo's observation. Moving on, again, the history of astronomy continued. Not far from here at Lick Observatory, a man named James Keeler was observing. He hand drew a beautiful picture like this with what was then the state-of-the-art telescope. And then moving on, the space age came and we took a gigantic leap forward in our understanding of Saturn and the rest of the solar system. Voyager gave us images like this, new close-ups of the clouds, beautiful detail of the rings. We discovered spokes, we discovered waves and other things going through the rings. So Voyager went past Saturn in the early 1980s, and it was only a few years after that that US and European scientists together started saying, we need to go back to Saturn and we need to have an orbiter. And it was a long process, and it's actually an exemplary story of international collaboration. But eventually the Cassini-Huygens mission was activated, science teams were selected. The science teams, numbers something more like 100 scientists, about 2/3 of them are from the United States and about 1/3 of them are from Europe, which is really unusual in science mission teams. So the international collaboration is a wonderful aspect of Cassini. Launched in 1997, flew past Jupiter in 2000 on its way to Saturn, and went into Saturn orbit in 2004. Once it got to Saturn, here is a timeline. So here, construction, you can see Saturn is about the size of a school bus. You can see some people down here for scale. Saturn is the largest interplanetary spacecraft that has ever been launched. Then here's the launch from Cape Canaveral, 1997. So you are now here, around where the Earth is. It took 7 years to get from Earth to Saturn. Went into orbit, skimming across the face of the rings to fire its rockets to put itself into orbit. And then we started the tour. And here is Saturn's path around the sun. Saturn takes 30 years to go around the sun. So you can take those 30 years and divide it down into months or seasons, the way we think about our single year at Earth. And if you do that, Cassini arrived at Saturn in Saturn January, and then stayed there for 13 years, and when the mission finished, it was Saturn June. So it was barely half the year, not even quite half the year, but it was actually one of the reasons why it was argued that we should have the mission extend for so long, so that we could see at least the seasonal cycle once. So very soon after Cassini arrived at Saturn, the Huygens probe, which was even a much more European-heavy component than the orbiter, the Huygens probe detached from the spacecraft and descended onto the surface of Titan, and found lots of amazing things. Titan is a landscape much like Earth, except that the chemistry is entirely reversed. Whereas here we have bay like this, liquid water flowing over a bed of rock. On Titan, they have liquid hydrocarbons, similar to what we burn in our stoves. And water is actually playing the role of rock. Water is frozen hard as a rock at Titan. Interestingly, we started in Saturn January and we made it all the way up to Saturn June. Saturn March happened in 2009. And that was a very special time for Cassini. We saw the equinox. Among other interesting consequences of spring coming to Saturn was that for a brief period of time, the sun was shining edge on to the rings. Saturn's rings are arguably the flattest structure known to humanity, where the distance is 300,000 kilometers from end to end, and the vertical height is not about the same as this room, maybe a little more, about 10 meters. So very, very flat structure, but there are some places where it's a little bit more puffy. There are also some places where it's corrugated, like a tin roof. And those kinds of structures cast shadows at the equinox. Here you can see the moon Daphnis and the longer shadow being cast by Daphnis, but you also see these vertical corrugations being excited by Daphnis and the way that they cast shadows too. That was one of the great features at equinox when the sun was shining edge onto the rings. Moving on then, we finally got to the ring grazing orbits and the grand finale, which occurred from December 2016 to September 2017, and that will be the main focus of our talk today. Cassini is a very capable spacecraft, has a dozen different science instruments, and many of them are here, particularly the main camera was bolted onto the side of the spacecraft here. There are also other instruments, including a infrared mapping spectrometer that took images, but not quite as high resolution as the camera, but every pixel of the image had over 350 colors, so that it could really do a lot of diagnostic chemistry of what was going on with what the Saturn system is made of. There's an ultraviolet spectrometer. The radio antenna was also used as a scientific instrument. Among other things, it was able to beam signals to Earth as the spacecraft moved behind the rings, and by looking at how the signal is changed by the rings, we can learn a lot about the fine structure. There are also particles and fields instrument. There was a dust detector that could measure dust particles as they impacted the spacecraft, a magnetometer, here's the magnetometer boom, radio and plasma instruments to detect the magnetosphere and the excited plasma of Saturn. Again, as I said, a primary reason why the mission was extended as long as it was to encompass a seasonal cycle at Saturn. What you see here is the hexagon at the north pole of Saturn, and the hexagon changed. Here it is in 2013, so this would be something like Saturn, April or May. And then here in June, as we get to the end of the mission, high summer, here you are seeing down into the atmosphere, seeing methane and other gases deeper in the atmosphere. But by summertime, a haze has formed over the hexagon, and so these kinds of seasonal changes give a lot of information to the atmospheric scientists. As they see not only what Saturn looked like at one moment in time, but following it over a long period of time.
What do they theorize causes the hexagon?
So I am not an atmospheric scientist, but the basic idea is it is a jet stream, and it has a sinusoidal component, and as it goes a little bit to the north and a little bit to the south, and goes all the way around like that, you end up with this cycle. This is a diagram of the orbital tour of Cassini. So Saturn is way down at the center of this diagram, and the different colors are different periods in time through the mission. Cassini was able to do as much as it was able to look at Saturn from a whole bunch of different viewing angles, as you can see from this diagram. And that's largely due to Titan. Titan is the largest moon of Saturn. It's one of the largest moons in the solar system. Titan is also fairly far from Saturn as moons go, so that means that it has a whole lot of angular momentum, to use a physics term. And what that basically means is that when Cassini flies past Titan, it's able to use the tugs that Titan gives to the spacecraft to change its orbit very efficiently. So they do use some rocket fuel to tune how it's going to encounter Titan, but it's really the encounters with Titan that really enabled it to get way up high above, so it could look down, face onto the rings and down onto the poles, but then also at some times in the plane of the ring system, so that it could get lots of encounters with the moons, which are mostly orbiting in the equatorial plane of Saturn. So this slide is intentionally way too busy for you to absorb. And my point is that Cassini is the most spectacularly successful mission that Saturn has ever flown, at least in my opinion. And the number of discoveries that I could talk to you about, we would be here all night. And maybe some of you would say, hey, let's go for it. But I prepared slides to talk mostly about rings, because that is my particular field of research. But Cassini has just done amazing discoveries. I already mentioned a little bit about Titan. There are lakes and rivers and sand dunes. It's a very familiar landscape with the chemistry being completely alien. There's Enceladus, where there are plumes of water coming off of the South Pole. Enceladus is the only place in the solar system that we know for a fact that liquid water and organic chemistry and sufficient energy are all in the same place, in contact with each other. There are other places that are of astrobiological interest. There's Europa, there's Mars, but other than Earth, Enceladus is the only place where it is known for a fact that those 3 building blocks for life are all in the same place, in contact with each other. So Enceladus is very interesting in that regard. The magnetic field, Mimas, Iapetus, Phoebe, all kinds of very interesting and fascinating discoveries have been made by Cassini. So, why did the spacecraft have to die? In a way, Cassini is a victim of its own success because Cassini was not engineered to the very exacting sterile standards that would be required to land on a location where there is astrobiology interest or there is possible habitability. And from Cassini's own discoveries, it turns out that Enceladus and Titan are now locations of astrobiological interest. And in order to prevent even the possibility that after engineers lost control of the spacecraft because its fuel for reorienting itself ran out, that Cassini might someday crash onto one of these worlds. They're not so much interested in needing to keep them pristine, as in just for the sake of keeping them pristine, but if we were ever to go to one of these places and find life there, we want as much as possible to exclude the possibility that that life came from Earth. And so that is why to just be as careful as possible, it was decided that Cassini needed to come to an end. And a very spectacular end was planned for it. If this decision hadn't been made, most of the discoveries that I'm talking to you about tonight would not have been made, because once the end of the mission was known for a fact and planned, they were able to take a little bit more risk. And they were able to dive right down in the middle of the main ring system and eventually send the spacecraft into the planet for its final resting place. So my next slide, I'm going to prepare you a little bit before I hit the advance, is going to show you a little bit of the orbital dynamics of the ring-grazing orbits and the grand finale. So, like I said, when Titan, when Cassini flies past Titan, that's when it's able to get a little bit of a kick to change its orbit, and you'll see that in the next slide. What you'll also see is down in the lower left corner, you'll see a pull-down view where you can see the distance of the Cassini spacecraft from Saturn, but the main window that you'll see is kind of if you were sitting in a cockpit seat right behind Cassini, kind of seeing a similar view to what the spacecraft saw. So here we go. So here is Cassini. So this is the last of the ring-grazing orbit. So Cassini is going to dive just off the outer edge of the main rings. Here we go. Ring flyby right there. Now, if you watch carefully, you'll see Titan come past. There's Titan. So Titan goes past Cassini, or Cassini goes past Titan, depending on your point of view. Cassini's orbit is now changed, and it is going to dive between the rings and the cloud tops of the planet. And so here we go. Hold on to your seats. There we go. We went between the rings and the planet. And so let the video end. So Cassini then did this 20-something times of these are called the grand finale orbits. The ring-grazing orbits were the ones where Cassini was just off the outer edge of the main rings. These are the grand finale orbits going between the rings and the planet. And then, again, you'll see Titan go past. It'll slow down, actually. So we had 22, I think, of these grand finale orbits. And then it slows down. There's Titan. Gives a kind of a distant flyby, changes Cassini's orbit again. It was the final goodbye, or the kiss of death, and Cassini descends down into the cloud tops of the planet to end the mission. So, like I said, there were 20 of the ring-grazing orbits from December of 2016 to April of 2017, and then 22 of the grand finale orbits from April to September. So again, you can see this geometry. Basically, as a ring scientist, we finally got to experience what the icy satellites people had been doing for the entire mission, which is, every now and then Cassini would make a close flyby of Enceladus or Titan or one of the other moons, and they would have this amazing flurry of activity to cram as much science as possible into the flyby. So we went through the first 12 years of the mission as ring scientists, having never experienced this, and then suddenly we were doing it every week, and we had to plan all of these amazing opportunities and try to make the most of it. So we got 42 of these close flybys of the rings within the space of a year, a little less than a year. Again, the ring-grazing orbits had the best viewing, as you can see, of the outer part of the main rings, whereas the grand finale orbits had the best viewing of the inner part of the rings. Also, the grand finale orbits had even more because you were descending into the upper atmosphere of the planet itself, and so you could actually, with the chemical instruments, taste what the upper atmosphere is made out of. The magnetic field instruments and the gravity instruments. We're just having a field day getting so close to Saturn, measuring a lot of its detailed structure that has it just isn't accessible when you're at the distances that you usually are. So among the things that we did, I'm going to show a little bit more of atmospheric science. So here is one of the descents. So you can see this strip of imaging as Cassini is descending down between the rings and the planet. This was a pass that was focused on the atmospheric science, taking all of these, this is just showing you the location. On the next slide I'll show you what they actually saw, but this is showing you just the location of all of the images that were taken. Here's how those images came out. You see the polar vortex briefly at the North Pole of Saturn, and then you see all of this detailed cloud structure. Much of this has never been seen before. Just an order of magnitude more detail on the clouds and storms of Saturn than has ever been seen before. We also tried to take some images that would just give you a sense of what it was like if you were sitting in the cockpit seat of Cassini, descending down between the rings and the planet. So here's an image that we pieced together. You can see it's pieced together of several individual squares that we've pieced together in this way. But this side, to your left, this is actually the planet Saturn, and these big stripes that you see on the planet are the shadow of the rings being cast on the planet. You're here in between, and then off to your right is the vast flat plane of the rings, and you are actually inside the rings from a vantage point that had never been seen before Cassini's grand finale. The next movie, I'm going to prepare you before I do the time step, hold on to your seat, is a movie. So as you're descending down, looking outward towards the rings, you'll see the rings actually collapse down to a line and then start to open up again as you descend through the ring plane as you're looking outward towards the rings. So here's the rings collapsing down, and then you can see briefly at the end there, that's the underside, the unlit side of the rings. Okay, I'm going to get a little bit more detailed into the science at this point, and I'm going to start with an overview of Saturn's rings and what we know about them. Saturn's rings are made up of countless particles, and each one of those particles is on its own orbit around Saturn. At the same time, these particles are so close to each other that they very gently bump up against each other sometimes, and their gravity also affects one another. So it's a complex system in that way. Many, many millions of particles, even in a particular vicinity. If you're going to do a computer simulation of the orbit of any one of these particles, you have to keep account of millions of other particles, and that's just the ones that are close enough to affect the orbit of the one that you want to study. So it's an orbital system, but it's also a very dense system. Chemically, it is made of surprisingly pristine water ice, with only a little bit of contaminating other stuff. The identity of that other stuff has been a subject of research and debate. It appears that it's possibly organic. Some of it could be silicate, basically rock. That is continuing to be studied. The size of each of these particles is, most of them are from the size of a marble to about the size of a house, maybe the size of this room. One of my little pet peeves is, don't ask me how many rings Saturn has. It's not countless tiny rings. You should think of it more as a disk. There are very few places where the disk is really entirely empty, where there are real gaps that might define one ring as opposed to another. Although there are many places where it is organized in a very concentric way, and there are some places where those concentric circles are lower, have less stuff than the concentric circles on either side. But it's really kind of greater or lesser. It's never just a total gap. And it's not like the different concentric circles that you could think of are rigidly unrelated to each other. There's a lot of radial transfer of movement, and certainly radial interaction in terms of collisions and mutual self-gravity and things like that. And we do see many kinds of structure in the rings. We see moons, especially moons that are outside the rings, are driving waves that are in the rings. I'll talk about that. We see moons that are clearing gaps, so the moons are embedded in the ring and they're clearing a gap around them. And then we also see collective effects, as I was just talking about, the collisions and the mutual self-gravity. So here's the kind of basic architecture. The A ring is the outer part here. The B ring is the middle. And the C ring is inner. The B ring is much denser than any other part of the rings. Between the A ring and the B ring is what's called the Cassini division. Not named after Cassini the spacecraft, but named after Cassini the guy, who back in 1675, so not long after Galileo, who's a contemporary of Christian Huygens, he was the first person to, with a telescope, like you amateur astronomers, noticed that there was a division. That Saturn's rings had two main parts, what's now called the A ring and the B ring, with Cassini's division in between them. The C ring was discovered in the 19th century as an inner appendage. It turns out that the C ring is also a disk, a ring region, about 10 times less material per unit area than the A ring and the B ring. And it also turns out that the Cassini division is also a ring region, and it's very similar to the C ring in its character. There is a D ring. The D ring is actually inward of the C ring, but it's a dusty ring, and I'm going to be focusing on the dense rings today. The F ring is a narrow ribbon just off the outer edge of the A ring, and it's a very dynamic place. There are large moonlets embedded in it, but we can't really see them because they're grinding up so much against each other that they are shrouded in dust. Most of the ring system actually doesn't have dust. Like I said, the particles are marble size and larger. The dust gets kind of vacuumed up onto to form a kind of a sandy coating of the larger particles. And if you do see dust, that tells you that there's exciting new things going on. Something is getting actively ground up. The F ring is one of those places. So many of the slides for the rest of the talk will have a diagram like this. So you see the A ring, the B ring, and the C ring, and with the Cassini division in between. And there will be an arrow here showing you where in the ring system is the particular thing that I'm talking to you about. Okay, so here's an orientation. Here's the Cassini division and the A ring. And there are 3 moons that we know about in the outer part of the A ring. What's called here the Encke gap has the moon Pan inside it. Even closer to the outer edge of the A-ring is the narrower Keeler gap, and the smaller moon Daphnis is in the middle of that gap. And then right off the outer edge of the ring is orbiting yet another moon called Atlas. And in the ring-grazing orbits, Cassini was able to get much more close-up images of these moons than had ever been seen before. So here is Daphnis, and Daphnis itself has interest to people who study small objects orbiting planets. But what I really want to point out here is the way Daphnis is sculpting the ring around it. And in particular, if you look closely, there's this little ribbon. You see that little ribbon there? That was completely unexpected. And it's just, to my eye, exceedingly beautiful. And what that must be is a little pocket, a little blob of ring material that got pulled out of the ring by Daphnis and is now spreading out on what you might call a streamline. Keep in mind that Cassini is only about 15 degrees above the ring plane, so as we're looking down, there could be vertical structure here. In fact, we know that this kind of wave in the edge of the gap, it's vertical as much as it's radial. So there's vertical structure here, but just a beautiful picture and also new intricate details. Zooming out a little bit, this is the same image, the same imaging sequence where we saw Daphnis close up. You can again see that little ribbon of material here next to Daphnis. And the color here it's exaggerated color. Instead of red, green, blue, it's actually infrared, green, and ultraviolet. But it's still, the rings do have a kind of a tan color that comes from contaminating material. But you can see also the structure that Daphnis is raising in the ring around it. After about the third wave crest, that structure begins to fall apart.
Does Daphnis move at the same speed as the ring material?
Yeah, so good question. So what about orbital speed? So this will come up several times in the talk. Kepler's second law says that the speed at which you go around the planet is uniquely determined by how far away from the planet you are. If you assume a circular orbit. If the orbit is eccentric, you have other things that go on, but it's still true that the average speed, even for an eccentric orbit, is uniquely determined by how far from the planet you are. So, going back to this, so Daphnis, everything is going to the right here, right? So Saturn is up, and Daphnis and everything is orbiting to the right. So that means the ring material that's inward of Daphnis is going faster than Daphnis, and the ring material that's outward of Daphnis is going slower than Daphnis. So if you just keep your focus on Daphnis, Daphnis thinks that this stuff is going ahead of it, and this stuff is going behind it. So you might ask, why are the waves only on the outward side? Well, that's because we just happened to frame this picture so that you see Daphnis and the stuff that's trailing behind it. If you were to reframe this so that you were looking a little bit more to the right, you would see the same kind of structure over here, ahead of Daphnis. So that kind of basic idea will pop up a bunch of times, so thank you for asking about it. So really, each of these waves is just one eccentric orbit, right? From here to here, it's just one orbit ago. Like this material is encountering Daphnis now. This material encountered Daphnis 1 orbit ago. This material encountered Daphnis 2 orbits ago. This material encountered Daphnis 3 orbits ago. And because the orbits are eccentric, sometimes they're a little closer to Saturn, sometimes they're a little farther away. So that's what creates these wave crests. And it's the third wave crest here where the ring material is starting to say, hey, wait a minute, who was that Daphnis that kind of kicked us around? We're actually more interested now in all of these ring particles around me and how I'm feeling this kind of gravity and stuff. So the waves that Daphnis had stirred up are falling apart and fragmenting as the ring particles are glomming onto each other instead of following the organization that Daphnis tried to impart. So I'm going to move on because I'm blabbing because this is such. All right, so here is Pan. Pan is amazing. So we knew before the ring grazing orbits that Pan had a kind of appendages around its waist. One of my now departed French colleagues memorably called them love handles. But what we didn't know is that, what we might call the apron around the equator of Pan is very, very thin, almost bladed, and it's very stiff. Look at this. You can see craters and grooved cracks. So it must be very stiff to be able to support that kind of structure. Some people think Pan looks like a ravioli. Atlas, on the other hand, you might think this picture is fuzzy or out of focus, but it's not. The apron of Atlas is actually that smooth. So what this tells us is that the apron around Pan, I think, must be older. It's had time to get stiff. It's not currently accreting new material, whereas Atlas is probably getting fluffy new ice particles falling onto it, burying any craters or cracks that previously were there. Atlas looks more like it's wearing an inner tube, whereas Pan looks like it's wearing a two-tube. You see them all together. And these can be explained, I think, possibly, and this hasn't been, I should write this down and see what my colleagues think of it, but my personal theory is that because Atlas is between the F ring and the A ring, material coming inward from the F ring is snowing onto Pan and keeping its apron fat and smooth, whereas Pan, did I say Pan? I meant Atlas. Whereas Pan is in a much more sedate area. The Inca gap is much better organized, and so there isn't a whole lot of new material falling onto it, so its apron has had time to stiffen. Anyway, so that's it about the ring moons. I'm now going to start talking about propellers. So propellers, it's the same concept as the moons, Pan and Daphnis, where they are orbiting in the middle of a gap. And I didn't get into this, but you might think it's paradoxical because gravity is an attractive force. So how do the moons clear away a gap? But it has to do with the fact that you not only have the moon and the ring particle, you also have Saturn. Orbital science is a very rich and intricate field because there's a lot of counterintuitive things that set themselves up. But when the moon pulls the ring particle toward it with gravity, the net effect is basically that the ring particle gets driven away because of the way it changes the ring particle's orbit around Saturn. So these are moons that are 10 times to 100 times smaller than Pan and Daphnis. So they're trying to do the same thing. They're trying to clear out a gap. They're making a disturbance. The ring particles around them notice, and the orbits of the ring particles are changing. But the disturbance doesn't get very far downstream before the ring particles basically forget that this movement had tried to push them around and just go back to interacting with each other, and the gap gets filled in. And so here again, we have Kepler's second law, right? On the inward side, you can decide which one it is, because this is a symmetric simulation. But on the one side, the disturbance on the inward side gets carried forward, the disturbance on the outward side gets carried behind, and you end up with this propeller-shaped type of structure. And so these moons are called propeller moons. So these moons are about 100 meters across. The big ones are maybe up to 1 kilometer across, whereas Pan and Daphnis are 10 to 30 kilometers across. So let's see. Oh, this is a simulation. We wish we could see the rings at this level of detail, but we're pretty sure that something much like this is going on. And you might notice this webby structure. I don't have time to go into much detail about that webby structure, but it's called self-gravity wakes, and it's basically as the ring particles are feeling each other's gravity, they try to clump together, but the tides of Saturn pull those clumps back apart as soon as they can form, and so the result is that you don't just have a homogeneous sheet of ring particles, you have this clumpy webby structure instead. Propellers are particularly interesting because they give us a window into baby solar systems. All of the pictures on this slide are from simulations of baby solar systems, protoplanetary disks. places where you have a massive object inside a disk of material, and so the massive object is interacting with the disk is affecting it, it's affecting the disk, and we aren't able to look at baby solar systems. We do now see some baby solar systems around other stars, but from very, very far away. There's nowhere near this level of detail. So we can't see this kind of thing around other stars. We can't go back in time and see what our solar system looked like when it was in this kind of a phase. But we can go to Saturn and look at what these kinds of processes looked like and how they worked. So in Saturn's rings, here again is the A ring, here's the Encke gap, here's the Keeler gap, and here's the F ring. It turns out that there are two regions where we see two different kinds of propellers. The propeller belts are in the middle part of the A ring, and we see swarms, lots and lots of small propellers. The central moons there are about 100 meters, so about the size of a football field. Between the Encke gap and the Keeler gap are what we call giant propellers. They are an order of magnitude larger, which means they're 1,000 times more massive, right? Because size goes as, the mass goes as the volume, the mass and the volume go as the size cubed. So much larger objects. They're also much more rare, which means that we can see them from farther away. And when we look at the same object weeks or months later, we can be reasonably confident that it's the same object that we saw weeks or months ago. Whereas over in the propeller belts, where they're all swarming together, there's really no way to know from one time to another whether we're actually seeing the same object we saw before. So the giant propellers have been even more scientifically interesting because we can actually track their orbits. And I'll talk about that in a little bit. First, I'm going to talk more about the propeller belts. This is going down memory lane for me. This was the first discovery of propellers. It's very, very grainy. You can see 3 of them here, and you can see these 2 little dashes, right? 2 dashes offset from each other. They looked very much like that simulation that I showed at the beginning, right? And so that's what we inferred, and we were right. Propellers had been predicted by some theorists, and this was how we saw them for the first time. Now, this was a very unusual image. As I showed you the Saturn orbit insertion, where Cassini was just skimming over the rings and looked straight down, very briefly, at very close range, and took these images. So much higher resolution, much finer detail than we were able to see for most of the rest of the mission. But because Cassini was skimming so quickly, laterally across the rings, we couldn't do long exposures. Any exposure of any length would have been so smeared that we wouldn't have been able to get anything out of it. So this is very, very low signal to noise. That's why it's so grainy. We first saw this, and I remember going on to an interview and saying, these are great, but we're never going to see anything like this for the rest of the mission because they're too small. And, I was wrong. And I'm glad I was wrong. But it turns out that there are lots of them. And so here's just one image, and you can see over a dozen of them, all of these little dashes, and we can see them just fine. But in my defense, this is the original discovery image at the same scale as the propellers that we saw for the rest of the mission. So the reason I was wrong is because what we saw was the small end of the size distribution, and there are much larger ones as well. So still, I mean, we're talking about, maybe it's 50 meters to 200 meters for the central moonlet. So they're all pretty small, but there's definitely a range of sizes. So this was about the quality of information we had on the propeller belts going into the ring grazing orbits. And what we got from the ring grazing orbits was this. Just much more beautiful detail. I'm not even going to have time to talk about spiral density waves in this talk. Spiral density waves have the same physics that cause galaxies to have spiral shapes, but the spirals are much, much more tightly wound at Saturn's rings. They occur when there's a resonance with the orbit of the moon, and I just need to move on. But that's what these spiral density waves kind of form a lot of the landscape that other things in the rings are kind of moving across. So this is a spiral density wave. You can just kind of think of it as the background for what I'm talking about for this slide. What I'm pointing out here are all of these propellers. And the fun thing is, the green square here, those are small propellers, just like what we saw in Saturn orbit insertion. That green square is the same size as the original image in which we discovered the first propellers. But here in the same image, we also see, such as over here, the larger propellers, like the ones that we saw after orbit insertion for the rest of the mission. But here we're seeing them in much more detail than we saw before. And so here, for the first time, we know how many big ones are there for each small one, and how big are the biggest ones compared to the smallest ones. Turns out that the big ones are 4 to 5 times bigger than the smaller ones. And that's going to tell us things about, what are these things made of? Where do they come from? What kind of fragmentation of some kind of parent body? And the range of sizes that something fragments into tells you something about what it's made out of. That's all analysis still to be done. Right now we're still in the, wow, this is amazing stage. But that's just a taste of what we've got here. Moving on to the giant propellers. As I said, these are larger and rarer, so both of those factors make them easier for us to track. These are some of the best giant propeller images that we had before the ring-grazing orbits and the grand finale. But I think the thing that has really caused the propellers to gain a lot of interest is that we actually do see their orbits change. So we're able to track the orbits because they're large and rare. And we see the orbits changing. So here you have from 2006, 2005 really, all the way out to 2017. This is the largest of the propellers. We nicknamed them after aviation pioneers because they're propellers. So this one is Blériot, named after the first man to fly across the English Channel in 1909. And we see these migrations. So look over here at the left-hand axis. So this is plus or minus a degree of longitude. This thing is going around Saturn once every 18 hours. Every 18 hours, that's 360 degrees. It goes all the way around. And for, 12 years, it's staying within plus or minus a degree of longitude. So overall, this is a very well-behaved orbit. But the excursions from that orbit, going ahead or behind, are clearly there. They're much larger than the accuracy of our measurements, and they're clearly organized. So why is Blériot sometimes going slower than that circular orbit and sometimes going faster, but only by a little bit? Are we seeing that it sometimes collides with another ring particle that changes its orbit? Are we seeing that it's interacting with the disk the way a baby planet would interact with its disk? That's a particularly interesting possibility. I think that sometimes what happens is the moon at the center of the propeller is accreting material, and eventually it gets so large that it can't actually hold on to all of that material, and so it sheds a big portion of itself in an asymmetric way, and that gives it a big kick that changes its direction. So that would explain these kind of more sharp changes of direction, but a lot of these are curved. The curvature tells you that something gradual is going on, and to me, that really implicates a gravitational exchange with the disk, which is the baby planet scenario. So I think we have the baby planet scenario punctuated by more catastrophic events, either a collision or a shedding event. So I think the answer is all of them. But this has really stimulated a lot of theorists, as well as being really neat observations. So this is showing us how is the disk affecting the propeller. It's changing its orbit. We also want to know how is the propeller moon affecting the disk. And to do that, we were able to do close flyby targeting of a few of the propellers in individual passes. Like I was saying, these ring-grazing orbits, once a week we were doing a close flyby of the rings. A few of those times, because we had orbits of where these propellers were going to be, we said, hey, this propeller is going to be pretty close by as we do the flyby. Let's get close-up pictures of it. So here's the propeller Santos Dumont. Here you see it from the lit side of the rings, and then on the same pass, so Cassini was looking down on the lit side of the rings, went through the ring plane, and then looked up on the unlit side of the ring. And I don't have time to get into why it looks different on the unlit side, but you see different patterns. And by putting these together, knowing that this is the same object being seen on the two different sides of the rings with different lighting geometries, we can learn even more about the basic structure. Here's another propeller. This is Earhart. It looks different from how Santos Dumont looked. So why is it different? We don't know. And then here again is Blériot, the king of the propellers, which we only saw on the unlit side. So you see this large area in the center where it's dark because there's too much ring material. It becomes opaque. So those were the beautiful close-up flyby images of the propellers. So moving on again to impacts. There are only a few places in the solar system where impactors have been caught red-handed. Obviously in the Earth, we see meteors from time to time. You amateur astronomers probably do that. Do you even, at this point, has the technology advanced where amateur astronomers can see impact flashes on the moon? Have any of you ever seen such a thing?
Yeah, I've seen a few videos of it.
I think it's pretty rare, but possible. Maybe if you really work at it. Obviously, Comet Shoemaker-Levy 9 and a couple of other objects have been seen to impact Jupiter, but that's about it. There's not a lot of places where we see, like, we've seen, for example, on Mars, we've seen, the orbiters are very, carefully mapping the surface of Mars, and they see a place where there was no crater, and then they come back a few years later and there's a crater. So that's seeing the cratering process and getting an idea of how often it happens. But I don't think a crater or an impact event has actually been seen in action at Mars. But we have seen it at Saturn, in the rings. And what we have here is the rings are acting like a detector, right? The rings are very, very large and very delicate. And so what they do is when an impactor crashes into the ring basically amplifies the signal so that we can see it. And what you see here, so most of the structure in the ring is concentric, or very close to concentric, as I was saying. The thing about the impact clouds is that they're slanted, they're canted to the rest of the ring structure. So you see this canted structure here, and this one here. This one here is very canted to the ring structure around it. And the reason for that is this. Again, Kepler's third law comes up. So you start with this, say you start with a circular cloud of material being thrown up, and I don't have time to go into why this is, but we are convinced now that this is not a single solid object impacting the rings, but an object that was previously pulled apart and a stream of material now orbiting Saturn from an object that was pulled apart. And so this stream of material crashes into the rings. You start with a circular cloud of ejecta. And then again, the ejecta on the inward side is going faster, and the ejecta on the outer side is going slower. And so the ejecta cloud shears out. And the great thing about it is the cant angle tells you exactly how long it has been since the impact. Right? I'm sorry, there's not a lot of equations in this talk, but the tangent of theta is p over 3 pi t. T is the time elapsed since the impact, and p is just the orbital period. So, so basically, we're able to say how old is this impact cloud just by measuring the angle. All right, you know what? I'm blabbering on, and I'm gonna. Right, fine. I'll talk about these later. The reason we see these in the ring-grazing orbits, there are some ejecta clouds that we saw during the equinox. That had to do with the fact that the ejecta is rising up above the ring plane, and the equinox, as I mentioned, highlights everything that's out of the ring plane. But the ring-grazing orbits, we are taking advantage of the fact that dust scatters light forward. And you can look, there's a light source over here. I look along the surface here. It's a pretty clean podium, so not a lot of dust. But if there was, you could see it, right? And you look towards a light source because dust scatters light in that way. And so, like I said, most of Saturn's rings does not have dust, but the ejecta clouds are full of dust. And so, if you can look almost towards the sun, you can see ejecta clouds more easily. But for most of the mission, we can't do that because there are infrared detectors on board the spacecraft, and if we look towards the sun, the infrared detectors would be destroyed and people would be mad at us. So we can't do that. But there's an exception. If the spacecraft is in Saturn's shadow, which is to say, if the sun is behind the planet from Cassini's point of view, then we can look towards the sun, or almost towards the sun, and look at the rings at what we call this very high phase angle. And so during the ring grazing orbits, we can be close to the rings and in Saturn's shadow. And so that's why we were able to get new images of these ejecta clouds. And here we see a whole bunch of them. And we were able to see them in color. And so this will tell us if they have a different color from the ring material around them. That will tell us about, again, the fragmentation, which will then go into telling us what things are made out of and kind of how much strength they have as they cohere together. Interestingly, we seem to see them in clumps. And this would support the idea that we are seeing streams of material impact onto the rings and not just single little bullets. So those are just a few things that we get from the impact structures. All right. You said an hour to an hour and a quarter, right? So I'm not doing too bad. All right. So ring textures. So we knew before the ring grazing orbits began that some places in the rings had these kind of textured character. And this is a place where you see a lot of structure. It's really pretty. I told you a little bit about density waves before. This is a density wave. This is a big density wave. This is another density wave. This is another density wave. And here you see almost a corduroy pattern, and that has to do with Pan is nearby. And Pan went by not too long ago and organized all of these ring particle orbits into this pattern. And what I'm going to do for the rest of this segment of the talk is, for each of these images, I'm going to rip out the center of it. And what I've done here is you take the, on a radial basis, so at every point here where you have, this is, every point here that's a concentric circle, right? This is all the same distance from the center of Saturn. You take the average brightness for each concentric circle and subtract it off. And that's what I've done in this central strip. And so what's left over is just stuff that's local. And so you see this clumpy, what we call straw-like texture, is really accentuated when we do this, what I call the radial filter. And so we knew that basically the troughs of the density waves have this kind of clumpy structure. So we'd seen it much more dimly in the very strongest waves. And this is one of the strongest waves. It comes from the moon Janus. And this is where ring particles are going around Saturn 6 times for every time that Janus is going around 5 times. And so these density waves are places where the ring particles get crammed up against each other, and then the pressure gets released again. It's kind of like a wave pool, if you go to raging waters or whatever they have. And so the ring particles are jammed up against each other, then the pressure is released again, and so they have been jammed up into these kind of clumps, and then the clumps kind of fall apart. And so that's kind of a very simple explanation of what this kind of straw structure comes from. So we knew that it was in the very biggest of the density waves. In the ring grazing orbits, we were able to see straw-like structure in much smaller density waves. That's interesting, kind of pretty. But then we started seeing it in places we never expected to see it. This is the inner A ring. This has a bunch of structure that we don't really understand. There's a lot of, we often talk about the stuff we do understand, because that's what we can say the most interesting things about. But there's also a lot of stuff that we don't understand. We have some ideas of what the structure comes from, but we don't understand much of the details. And it turns out that this one little belt here has clumpy straw-like structure, but on either side of it, it doesn't. And it has nothing to do with density waves. It's hard to tell because of all this other structure, but there is actually a density wave here, and there's another density wave here. This one has maybe some kind of straw-like structure. This one has none at all. And then the straw structure is over here where there's no density wave. So that's very strange. We go over here now to the C ring. This is what's called a plateau, where these are these are sharp-edged and much brighter than the surrounding sea ring. And it turns out that the plateaus have this streaky structure, which is very different from the clumpy structure. And then outside the plateau, you have places here where there's clumpy structure, and then right next to it, you have places where there's no texture at all. So what are these textures telling us? Well, they must have something to do with how ring particles are interacting with each other when they collide. Right? And so that goes to not only what are the ring particles made of, but like structurally, what are they made of? Are they piles of rubble, or are they more frosty? Do they have kind of gravelly surfaces, or are they more slick? Those kinds of differences will make a difference in what happens when two ring particles collide with each other. And again, this is another one of the things where we are in the gee whiz stage of scientific discovery. And the actual analysis where we figure out what is going on is to come. And this is obviously how science often works. Cassini has answered a lot of scientific questions that we had before the mission began, and as it does so, it brings up even new questions that we never thought to ask. This is a fun picture to show, largely because it's pretty, but it's also kind of neat to think about. So this is another one of these spiral density waves, and this one is in a location where the waves don't damp for reasons that we're maybe starting to understand. So the damping is suppressed. And so this wave just rings on and on up towards the upper left of the image. And the other great thing about this is Janus is a moon that actually shares an orbit with another moon. And every 4 years, the moons start to come together and they actually trade orbits and drift apart again. And wow, orbital dynamics is so fun. But that happens every 4 years, and every time that happens, the rate at which the moon is going around the sun changes because, again, Kepler's third law. And so that means that the location of exactly where in the rings this wave is getting generated changes just a little bit. So you see, if you look carefully, little glitches in this wave. Here's a little glitch, here's a little glitch, and there's more glitches going up there. And so the distance between glitches is 4 years of the wave propagating outward. So if you think about it, up here, we're seeing a bit of the wave that was generated around the time I was born, before Janus was even discovered. So it's kind of a fun way of thinking that not only are the rings dynamic and always moving and interesting in that way, but they also sometimes are able to encode history, and sometimes can even tell us things that we wouldn't know otherwise, like exactly whether Janus just popped into existence right before we discovered it. No, it didn't, because it was generating this wave. So I'm finally going to move on from talking about main camera images of the main rings. And main camera images of the main rings is what I studied, so I've kind of indulged in mostly focusing on that. But I'm going to give you a little bit of flavor of other things that we saw. Here is Saturn in the infrared, and this is false color. But what they've done to put this image together is blue is a wavelength that is reflected by water ice. Green is a wavelength that is reflected by methane gas. And red is a thermal wavelength that comes from deep inside the interior of Saturn. Right? So the sun is mostly behind Saturn in this image. We are looking at the night side. And so the rings are blue because they're very rich in that wavelength that is reflected by water ice. The reflected sunlight is the green up here being reflected off of the methane clouds. And then the red is the night side of Saturn. If you were looking in visible wavelengths, this would just be black. But in the infrared, you see the glow from deep inside Saturn. And then the black pattern is actually the clouds that are above that thermal glow that are blocking it in certain locations. So infrared really can give us a lot of information that we don't otherwise get. This is again a accentuated color image, also looking at the infrared. So you see this little slice. So this is a diagram of the ring system and giving you context for this little slice, which is also blown up over here. VIMS is the Visual and Infrared Mapping Spectrometer. That's the infrared spectrometer. ISS is the Imaging Science Subsystems main camera, which is what we've mostly been talking about. So what you see here is the B ring is more blue, which means it's richer in water ice. It's poor in the contaminant. Whereas the C ring and the Cassini division are quite red, so they have a lot more per unit mass of rocky organic gunk, giving it extra color. And then the A ring is in between. It has this tan color, so it's kind of intermediate in that way. Other things that we were getting out of the grand finale, there are things that don't lend themselves to pretty pictures, right? The gravity. So as Cassini was passing between the rings and the planet, they very carefully measured the radio signal as it was beaming back to Earth. And they could do the Doppler tracking of how the wavelength of the, it's the fire engine effect, right? The fire engine comes towards you, and then it goes past you, right? It's the Doppler effect, because when something is coming towards you, the wavelength is a little bit different from what it is when it's going away from you. And by tracking that very closely, the engineers were able to measure exactly how hard the gravity of Saturn was pulling on Cassini. And so we are able to probe into the interior of the structure, the interior structure of the planet, but also because for the first time Cassini was passing between the rings and the moon, the rings were pulling in the opposite direction. So they were able to pull out the signal of the rings' mass, and so to directly measure the mass of the rings. And this is important because there is an ongoing debate about the age of rings. And I mentioned that the rings are surprisingly pristine water ice. And the problem with that is that there is constantly meteoritic material falling onto the rings, which is not water ice. It's rocky, organic gunk. And even if you started with completely pure water ice, you can only have that meteoritic material falling onto the rings for so long before they would look dirtier than what we see them to be. Now, if the rings are very massive, that would allow for them to be older because you have more water ice to begin with that can better hide the pollution. But if the ring mass is relatively low, then you don't have that, and that would drive you towards the conclusion that the rings are young. With respect to the solar system, right? We were talking about 100 million years instead of 4 billion years, but still that's pretty remarkable for us, something to be that recent on the solar system scale. Also during the grand finale, chemical samplers tasted the environment of Saturn's atmosphere and were able to measure the chemistry of ring particles, at least tiny dust-sized ring particles. And the radar, which is mapping the surface of Titan, was close enough to the rings that they were actually able to acquire the rings with a radar signal, active radar on the rings, and doing new science that had never been done before in that way. Some of those, this is hot off the presses. In fact, it's not even on the presses yet, so this is some of the imaging results too, but also this is new stuff. Like, this has not yet been published, and so the talk will be available a couple months from now, and not tomorrow, on the recording. The tentative conclusion for the mass of the rings is that the mass is indeed low, and that is driving us towards the conclusion that Saturn's rings are probably 100 million years old, give or take, and not as old as Saturn. There's a lot that's actually fitting together with other lines of evidence that maybe the moons are young too. And this doesn't necessarily mean that we're living in a special time, like Saturn spent 4 billion years with no rings, and then just in the last 100 million years, the rings popped up and suddenly here we are to see them. But Saturn could be doing it could be more of a dynamical process. The moon system and the ring system may be periodically collapsing and blowing itself apart and then recycling. So the current incarnation of it, at least, is probably young. The chemical samplers, and this was again another completely unexpected discovery, but they found methane in the high atmosphere of Saturn, way higher than atmospheric methane should get blown from the lower atmosphere. So they are really driven towards the conclusion that methane is falling inward from the rings. And we don't know how that could be happening. But again, this, new discoveries raise new questions. So finally, a fun picture here. Here again you see, this is the Keeler gap, the A ring, the F ring, and you are here. You can actually see, this is the Earth and this is the Moon, kind of nestled in the arms of Saturn's rings. Let's see if we have, it's only a couple minutes, I will show my video. This is just a montage done by JPL of a number of the discoveries, just to give you another smorgasbord of things. Briefly, I have two more slides. I was just talking about whether Saturn's rings are there because we're living in a special time, and that's a conclusion that scientists always try to avoid because we try to explain things by natural processes, but I have been living in a special time. It's been an amazing privilege that this phase of my career has coincided with the Cassini mission, and when will we go back? When Juno finishes up its mission to Jupiter, for the first time since the 1970s, we will not be getting any radio signals from the outer planets. We do have new missions that will be arriving in the mid-2020s. The Europa Clipper is being planned. Europe is planning a Jupiter Icy Moons Explorer. Those are Jupiter, not Saturn, but they're great spacecrafts. Other concepts are on the drawing board. I have already been involved in some to go back to Saturn's rings, also some to go to Uranus and study its rings and other aspects of the Uranus system, and Neptune as well. There's lots of amazing things to do. There are more focused missions that want to just study Enceladus or Titan. Like I said, I have a Saturn rings skimmer concept that I've been involved with. I'd really like to see that fly someday before I retire. In the meantime, we have space telescopes, we have Earth-based telescopes, we have all of you amateur astronomers helping us keep track of what's going on at Saturn. We have the data set. Cassini has given us riches that we will continue to mine for a very long time. And then finally, I'm the one who's been standing in front of you giving the talk, but Cassini was an amazing team effort and just a great privilege to work with. This is just the imaging team and all of the other members of the Cassini team. So thank you very much. I saw a question here, a question here. Here, this one first, sorry. Sure, yeah, was there danger when we were crossing the rings? Yeah, absolutely. So, to some extent, because we knew we were ending the mission anyway, they accepted a higher level of risk, but they also did really look at it as much as possible. And a friend of mine, Matt Hedman at the University of Idaho, was leading that effort, studying the D ring, which is the dusty ring that I didn't even have time to tell you all the neat stuff he's discovered. But he was also looking very carefully at the profile of brightness and how it is diminishing and whether there really is an empty gap that we can fly through safely. And you're going 15, 20 kilometers per second. So a single piece of sand could kill the spacecraft. So yeah, they engineered that as much as possible, and they got the level of risk down to what they were comfortable with. Yes, you had a question too? Yes, the North Polar Hexagon. The South Pole also has a vortex. I guess the Earth atmospheric scientists don't like it when we say hurricane because it's different. But there's a kind of a vortex at the center of the hexagon, and there also seems to be a vortex at the South Pole. But there's no hexagon at the South Pole, only at the North Pole. Oh gosh, okay. You, and then right next to you there, and then
You said that you wanted the mission to last long enough so you can see the changes in the seasons. You see something like, for example, the change in the hexagon. But how do you know if you have less than one Saturn year, how many of these changes actually have to do with seasons or not just transient changes?
That's why we need to go back. Absolutely. We saw changes over the life of the mission, but how do we know that they were seasonal changes? How do we know that they weren't just, things changing on a longer time scale or, yeah.
Do you know that the hexagon change is because of the seasons?
I think they have a pretty good narrative that has to do with the heating of the atmosphere forming a haze that seems to hold together. Yes?
About those chemical samples. I heard a lecture once that suggested that a useful way to look for pre-life processes would be to see whether chiral molecules occurred in unequal proportions. And this lecture specifically mentioned Saturn's atmosphere as a good place to look. Is that something that Cassini was able to do?
So you're looking for chiral molecules and imbalance, just repeating for the rest of the group, as a way to search for life, and Saturn's atmosphere might even be a place. Cassini was not equipped to do that. Cassini had a mass spectrometer, so it was able to tell the atomic mass of particles that it detected. But it couldn't even tell the difference between, was it like methane and nitrogen have the same atomic mass? Am I right? I'm pulling that out of me. That's not right. But there's carbon monoxide and nitrogen. Isn't that right? Carbon monoxide and nitrogen have the same atomic mass. Cassini can't tell the difference between them. So it certainly was not able to detect chirality. Yes? Thousands of kilometers between the inner reaches of the D ring and the cloud tops. Yeah. Yes, sir.
How long did it take to send a command signal from here to?
Yeah, so so it depends on where Earth and Saturn are in their orbits, but In general, about 80 minutes. So good, what I always remember as a rule of thumb is that Earth is 8 light minutes from the sun. So if the sun were to explode, we wouldn't know for 8 minutes. It kind of, the outer planets fall on round numbers of astronomical units away. Jupiter's at 5, Saturn's at 10, Uranus is at 20, Neptune's at 30. So Saturn's at 10 astronomical units, so 8 minutes times 10 is about 80 minutes. You know, sometimes more or less depending on what side of the sun the Earth is on. Yeah, no, the engineering is just astounding, and I am always exceedingly grateful to the engineers who pulled that off. Yes. Does Jupiter have an impact on Saturn? So you're getting into orbital dynamics, which is actually like the details of, like, I could geek out on you for a long time, but yes, but not in a way that affects stuff orbiting Saturn. It actually does affect Saturn itself. There's actually a 5-to-2 near resonance. Jupiter and Saturn are close to being, Jupiter goes around 5 times when Saturn goes around twice. And there's actually some motions due to that near resonance that you can detect in the orbits of Jupiter and Saturn. And even in other planets, like because Jupiter and Saturn are pushing around the rest of the solar system. But that's a pretty weak effect compared to the moons of Saturn and the equatorial bulge of Saturn. Those are really what govern those. So you, the CA hat, and then you can ask a second.
Okay. If you were going to have another mission, what new instruments would you put on?
If you're going to have a new mission, what instruments would you put on? So it depends on what you want to do, right? You have to have a focused science goal. So Cassini was like just it's like the cafeteria, like the smorgasbord, right? It did almost everything. And it's hard to make a case for just doing Cassini 2, because NASA's always wanting to do something new and, you know, not just an incremental, a little bit better than what was previously done. So, you know, if you're going to Enceladus, you want more sophisticated chemical laboratories. You detect those chiral molecules and so forth. If you want to skim across the face of the rings, maybe you want to do that really cheaply so that you can be more focused with a smaller amount of money. So, like, our concept basically had a camera and a dust detector and nothing else. Not because you wouldn't want a magnetometer, but because the magnetometer gets so expensive that people start to say, well, we're paying all this money, how, you know, is it really worth it? So there's a kind of a competitive, right? This is all kind of human engineering and politics, where you have to come out with your concept, we're going to do this much science for this much cost, and so you have to figure out where you're going to pitch it. It's more that kind of stuff.
If money was no object, though, what would you
Oh,
put on?
I mean, if money is no object, you just send everybody.
What would you put on, though? Like if you sent something out?
Well, okay, if money was no object and I could do this ring skimming orbit, I would definitely want the camera and the dust detector and, you know, infrared detector to get, you know, really fine detail on the chemistry and a magnetometer to get really fine detail on the magnetic stuff. I mean, you could drive yourself crazy with it when it was not. Yes. Yes. So my institution is the SETI Institute. That is my employer. And so as the person speaking, I took the liberty of putting my employer's insignia up in the upper left. So Cassini is organized, the way these missions are generally organized is the scientists come from all kinds of institutions. So the engineering for Cassini was done at JPL, but the scientists are from all kinds of institutions. So I was, for most of the Cassini mission, I was at Cornell University in upstate New York, and I moved out here 3 years ago. The SETI Institute does all kinds of science, not just searching for extraterrestrial intelligence. That's actually a very small fraction of what the Institute does, although it is part of our identity and obviously what we're known for and named after. But the Institute does a lot of habitability research. Where could life exist? There's astrobiology. You know, how could life have formed in different ways. And then a lot of just general planetary science, exoplanets, planetary formation. So we're a scientific institution.
The ultimate money for SETI come from tax.
Currently, NASA does not fund SETI research, which is the actual searching for extraterrestrial intelligence. Whether or not they should is a different conversation. All of the money that funds my salary comes from NASA or the National Science Foundation, and that is for science research and science education. It has nothing to do with me. In the back.
For telescopes, scientists have to apply on an annual basis for a specific project. Is Cassini set up in the same method, or is these projects defined way in the beginning so they know what instruments to put on there and what time to do the flybys and all that stuff?
Yeah, so NASA, there's different ways you can get money from NASA to do research projects. If you're just doing a research project, yeah, you usually have a 3-year proposal that funds just part of your salary for 3 years, and so yeah, that's very competitive and it's very uncertain. Missions are a more stable form of money because if you get picked onto the mission team, you're on the mission team for as long as the mission is operating. And so, my mentor, Joe Burns, who's here, he was picked to be on the imaging team in 1990. And, that source of support held steady for the entire, before the mission got to Saturn, I think the support was much smaller because you weren't doing it as much, but, there is more security in space missions than there is just to research.
Does Jodie Foster still work for SETI?
So Jodie Foster, you're referring to the movie Contact. We're actually very proud of the movie Contact. So Jodie Foster obviously never worked for the SETI Institute, but the lady on whom Carl Sagan based the character is Jill Tarter, and she is one of the founders of the SETI Institute, and she is still at the Institute, although she is now emerita, and she is someone we're very proud of.
Never looked at Saturn the same